Chemistry and you are watching Chem Science.
Let's discuss A-Levels question paper 4-2 of the examination series 9701 Chemistry May-June 2024. In this video, we'll be discussing first 3 questions in this video, and then later on in the next videos we'll be discussing the next questions. So let's start here. So starting with question 1, it says describe the trend in the solubility of sulfates of magnesium, calcium and strontium, and we know that's in chapter 1, that is lattice energy, that the solubility of the sulfates decreases down the group 2. So according to that, first comes the magnesium, then the calcium, because calcium comes next in the group 2, top starts with the magnesium and then strontium. So this is the trend. Least soluble is strontium sulfate and the most soluble is magnesium sulfate, followed in between by calcium sulfate. Now describe, that's the description, but explain. Explain means give reason. Now if we talk about reason, we know that the cation size increases down the group. So starting with that, we can write that as cation size decreases down the group 2, decreases down the group 2, decreases down the group 2. We can say that the lattice energy and hydration energy both, that is the enthalpy of hydration and lattice energy, both decreases down the group, or we can say that both becomes less exothermic, because the negative value decreases down the group. So we can say that becomes less exothermic, or you can say decreases down the group. But hydration energy decreases with greater value, decreases with greater value than lattice energy, So what happens is enthalpy of solution, let me write enthalpy of solution becomes less exothermic, Now we need to know that for a substance to become more soluble, the enthalpy of solution should be negative or should be a very small positive value. So if it becomes less exothermic, obviously the solubility decreases, down the group. That's the main reason, and we need to explain these 3 points, that lattice and hydration, both the energy decreases, becomes less exothermic, but hydration decreases more. Because of that, the enthalpy of solution becomes less exothermic. So let me finish my sentence: decreases down the group 2. So that's how we explain it, and as it's 4 marks, so we need to explain it in detail. Also we have got enough space to write everything, so I'll utilize the whole space and keep on writing the whole sentences in a proper way. Now the next is define lattice energy. So let me start by writing that it is the enthalpy change. It is the enthalpy change. You can even write energy change, but I better prefer writing enthalpy change when 1 mole of a compound, 1 mole of an ionic compound, 1 mole of an ionic compound is formed, from its gaseous ions. Now this is very important. You need to write gaseous and ions in standard condition, conditions. That is most important. So 1 mole is important from its gaseous ions is important. So this is definitely required for 2 marks. Now next question says, state and explain the main factors that affects the magnitude of lattice energy. Now to explain this, let's first try to understand what exactly is lattice energy. For example, there is an ionic compound, then obviously we have one positive and one negative at least in the ionic compound. Now lattice energy magnitude, that is the force of attraction between the positive and the negative ion, and that is the reason that the magnitude depend on certain factors. Now what are these factors on which the magnitude of lattice energy depends? Now that depends on the size of these ions. If the size of these ions is smaller, then this force of attraction between the positive and negative will be greater, and that's the magnitude of lattice energy will also be higher. But if the charge if you talk about, that also affects the magnitude. So if the charge is greater, that is in place of positive and negative 1, if it's positive 2 and negative 2 ions, then obviously the force of attraction is greater. So again, the magnitude depends on these two factors, that is the size of the ions and secondly the charge of the ions. So state and explain the main factors are, the first one is the size of the ion, the size of ions, and we can write smaller the ions, greater is the magnitude, of lattice energy, right? This is the first factor. Or even you can say more exothermic in place of magnitude of a lattice energy. Fine. The second factor is, as we say, the charge of the ion. So we can say that as the charge of the ion increases, the charge of the ions increases, greater is the magnitude of lattice energy, or you can also write that charge of the ions increases, more exothermic is the lattice energy. And here, as we have described, state and explain, so we are giving the reason also that how does it affects. So 2 marks is for the two factors being stating and explaining both. So we need to explain and state the factors. Okay, let's go ahead with the next part, where we have got a table of various energies, the enthalpy values, and here is a Born-Haber cycle can be used to determine the lattice energy of ionic compounds, and complete the Born-Haber cycle in figure 1.1 for potassium sulfide, that is K2S, in solid form. Include the state symbols for all the species given here. Now we can see that the dashed lines are given here, starting with the potassium in solid form and sulfur in solid form, and here we are ending up with 2 potassium ions and the sulfur and 2 electrons, and all this is the cycle. Now obviously K2S is a solid here, so let's start with the first step here, is that the atomization of both the elements. So atomization is, we are using 2 potassium, but that has to be atomized into gaseous form. So solid is changing to gas, that's the only thing. In the first step, we are dealing with only one element, so the sulfur remains as such. Now in the second step, now I'm writing the potassium in gaseous state as same as in the earlier step, but now the sulfur has changed to gas, that is the atomization of sulfur is happening. Now both the elements are in gaseous form. Now that has to be changed into ionic form in the coming steps. So in the first step, we can say that we can see that the potassium has changed into its ionic form in the gaseous form, but sulfur is still in its elemental form form with 2 electrons being lost by the 2 potassium ions. So the next step is that the sulfur is gaining 1 electron. So let me write first the potassium ions as such in the gaseous form and 1 sulfur in the -1 form, because altogether in the first step it's going to gain only 1 electron. So we are again left with 1 more electron and the sulfur is again in the gaseous form. So actually it's sulfide 1 ion in the gaseous form with 1 electron left. Now in the next step again the potassium ions will remain in the gaseous form in the same as in the earlier step, but now sulfur has gained 1 more electron, so it has changed into 2- form again in the gaseous form. So this is how we have completed all the dashed lines in the question shown here. So let's see the next part. What is the next part is calculate the lattice energy, that is delta H lattice of K2S using the relevant data from the table 1.1 and show your working. So let's first start by writing the formula, that is the lattice energy is the enthalpy change of formation minus the whole cycle. The whole cycle is that first the enthalpy change of atomization of potassium, then the enthalpy change of atomization of sulfur, then the enthalpy change, or you can say ionization energy of potassium, but we'll multiply that by 2 because the potassium used are 2 potassium ions. So multiply by 2 plus the first electron affinity of sulfur plus the second electron affinity, that is EA2, this is EA1 of sulfur. So that is the whole cycle that has to be subtracted from the enthalpy change of formation. So now let's substitute all the values. Now you can see that I have substituted all the values, that is the enthalpy change of formation is minus 381, the atomization of potassium is 89, which I have multiplied by 2 because we have used 2 potassium atoms. The atomization of sulfur, that is 279. The first ionization energy of potassium is 419, again that has to be multiplied by 2 because we have used 2 potassium ions. The first electron affinity of sulfur is minus 200, the second electron affinity of sulfur is plus 640. So that's the substitution of all the values, and the answer is minus 2116, and that is in kilojoules per mole. So let's substitute that here. I'm not writing the unit in the bottom one because the units are already written. So it carries 2 marks because you need to show the correct substitution and your working, and your final correct answer will gain you 1 more mark. So 1 mark for correct substitution and the second mark for the correct answered value. Let's go ahead with the next question. Here the question 1 ends, and let's start with the question 2 here. Question 2 is, first A part is lithium nitrate decomposes on heating in a similar way to group 2 nitrates to give a metal oxide, a brown gas and an oxygen. Write an equation for the decomposition of lithium nitrate. Now the brown gas is NO2 gas, that is nitrogen dioxide is a brown gas which is formed on the decomposition of nitrate. Any metal nitrate we get metal oxide also and oxygen gas also. So let's first start by writing the equation, that is LiNO3 that decomposes into the lithium oxide, that is Li2O plus nitrogen dioxide plus oxygen. Now if we start balancing it, here is Li2O, but then oxygen we have got 3. So if we balance it, we have got 4, 2, 4 and 1 here, and that's how we can see that there are 4 lithium atoms, 4 nitrogen, and the remaining oxygen are balanced as 4 into 3 is 12, and you can see there are 12 oxygen atoms on the other side. So this is how we have balanced it. You can even do in the other way, that is 2 lithium nitrate into 1 gives 1 lithium oxide, 2 nitrogen dioxide and half oxygen gas. That also can be done, which is written also in the MS, but this is also allowed. The second part is the other group 1 nitrates MnO3 decomposes on heating to form a metal nitrite, that is MnO2 and oxygen. The thermal stability of these nitrates increases down the group. Suggest why the thermal stability of any metal nitrate increases down the group. Now, metal nitrate thermal stability increases down the group in the sense it needs more temperature to decompose into the given compounds going down the group. That is, the compounds at the bottom needs more energy for the decomposition, and that is from that you can conclude that the N and oxygen bond, that is NO bond, should get stronger, and that's the reason it needs more energy to break down this bond, and so the thermal stability increases. And as we know that the cation size increases down the group, so first let's state that main reason, that as cation size increases down the group, what happens because of the increased cation size is that the ion polarization decreases. The ion polarization decreases. And that's the reason that the NO bond gets stronger. The NO bond gets stronger, which requires higher temperature, to break down. Higher temperature. I'm ending up here because that's the thermal stability, and we have already described that the NO bond gets stronger. So this is how we are going to describe in the 2 marks question. The first thing is the cation size increases, and the second point is the ion polarization decreases, making NO bond stronger. Okay, let's see what's the next question. Okay, here we have probably a numerical that acidified manganate ions, manganate 7 ions, that is MnO4 minus, can be used to analyze solutions containing nitrite ions, that is NO2 minus, by titration. So X is a solution of NaNO2. So we know that the X is a solution of sodium nitrite. Okay, sodium nitrite, NO2 minus solution. 250 centimeter cube of X is added to 50 centimeter cube of 0.125 moles per dm cube acidified manganate. Okay, the manganate ions are in excess. All the NO2 ions are oxidized in the reaction. The unreacted MnO4 minus requires 22.50 of 0.04 moles per dm cube of Fe2 plus ions to reach the endpoint. The relevant half equations are given here. Calculate the concentration in moles per dm cube of sodium nitrite in X. Now let's understand what is happening. First, we have reacted the X solution with the manganate solution, which is in excess. Now it's written it's in excess, and after the reaction, whatever manganate ions are left over, that are reacted with the Fe2 plus ions to find out how much of manganate is left, and that's how we indirectly calculate the concentration of X. So in that case, first we need to know that how many moles of manganate ions we had taken initially and how many are left after the reaction. So starting with that, first let's calculate the initial concentration. So I'm just writing the concentration MnO4 minus initial. That's how I'm writing it in short. The moles of, this has to be moles. So I'm writing N. Now moles of MnO4 initial, for that we have to multiply the concentration into volume. Now the concentration is 0.125 into the volume is 50 centimeter cube, which if we convert into dm cube, I have to multiply it by 10 power minus 3. So that is 6.25 into 10 power minus 3 moles. Okay, now let's understand how many manganate moles are left over after the reaction. To find out that, first we need to calculate the moles of Fe2 plus U. So moles of Fe2 plus used is again volume into concentration. So concentration is 0.040 multiplied by 22.50, again changing into dm cube we have to multiply it by 10 power minus 3. Answer is 9.00 into 10 power minus 4 moles. Now if you have a look, you have the equation with 1 electron here and the equation with 5 electron here. So if you balance the electrons and make the overall reaction, you have to multiply this by 5, so as the electron gets balanced and it gets cancelled off. So if you write an overall reaction, you will see that the manganate to the Fe2 plus ratio is 1:5. So if we want to find out the moles of MnO4 minus left over, then we need to divide the moles of Fe2 plus with 5. Okay, so divide it by 5 because the ratio is 1:5. So the answer is 1.8 into 10 power minus 4. So what we need to find out is now how many moles of manganate had reacted. So for that we need to subtract the initial moles and the leftover moles. So for that we need to subtract these two values, that is 6.25 into 10 power minus 3 minus 1.8 into 10 power minus 4. Now I prefer writing it to 3 significant figures, so I've added this 1.80, and so the answer is 6.07 into 10 power minus 3. So these are the moles of manganate ions that reacted with the nitrite ions. That's how the reaction occurs. And now again, if you have a look to these values, these two equations, and if you make an overall equation by balancing it, we can see that there is a ratio of 5:2. So here you will have to multiply by 5, and here the whole equation has to be multiplied by 2. So there is a ratio of 5/2. So from this equation we can find out the moles of nitrite ions by multiplying the moles of manganate ions with the ratio of 5/2. So multiply, so here multiply by 5/2 ratio. So I hope you understood the reason that to balance the electrons and to make an overall reaction, we multiply the manganate equation, half equation, by 2, and we multiply the first equation of nitrite ions with 5. So there is a ratio of 5:2, and therefore if we want to find out the moles of nitrite ions, we need to multiply the moles of manganate ions by 5:2, that is 5/2, which is 1.517 into 10 power minus 2. Now we know that these are just the moles. Now what is concentration? So concentration is moles divided by volume. Now the volume is 250 centimeter cube. So let's calculate the concentration, that is moles divided by volume. So that is 1.517 into 10 power minus 2 divided by the volume, that is 250, but 250 again has to be multiplied by 10 power minus 3, and let's find out the concentration then. So I got the answer as 6.068. Now if I write that 6.068 into 10 power minus 2 in 3 significant figures, I'll write it as 6.07 into 10 power minus 2 moles per dm cube. So this is how we got the concentration. It's a very indirect method, but you can see it carries 3 marks. Obviously there are long steps to calculate the concentration. Now let's go ahead with the C part, where the table 2.1 shows electrode potentials for some electrode reactions involving manganese compounds. Now there is a table, big table, but let's go ahead and see the question. Aqueous manganate 6 ions, that is MnO4 2 minus, it is, remember it is 2 minus, are unstable in acidic conditions, that is in the presence of H plus ions, and undergo a disproportionation reaction. The E cell of this reaction is 1.14 volt. construct an overall ionic equation for this disproportionation reaction. Now what is a disproportionation reaction? Is that the manganate 6 ions undergoes reduction as well as oxidation. Now if we are talking about MnO4 2 minus, let's have a look at the ionic equations which we have already got here. Is MnO4 2 minus is used here, okay, and here. There are 3 ions where we have 3 equations. It's used MnO4 2 minus, and we need to find out 2 equations where in one reaction it is getting reduced and in the other reaction it is getting oxidized. So here you can see that the MnO4 is changing to MnO4 minus, losing 1 electron. So this is oxidation, which is here written in the reverse form. So no problem, it's an oxidation reaction. Now this is the reduction reactions where MnO4 2 minus is gaining electrons to form MnO2. So out of these two, we'll have to select one. Now as we have already seen that in acidic condition is undergoing a disproportionation reaction, so we'll have to choose the equation with H plus ion. So this is the equation we'll choose. Okay, so this is the reaction we'll choose for the reduction, and this is the equation we'll choose for the oxidation. Now they have given a hint that the E cell of these reaction is 1.14. So if you subtract these values to find the E cell value, you will get an answer of 1.14. So obviously the two half equations which we have selected are correct. Now we need to make an overall ionic equation. Now so starting with this, let me first write this reaction which is already we have chosen, that is MnO4 2 minus plus 4H plus 2 electrons gives MnO2 plus 2H2O. Okay, again if we choose the oxidation reaction, then this is the reaction which we'll have to write it in the reverse form. So again MnO4 2 minus gives MnO4 minus plus electron. Now again, as I had discussed earlier also, we need to balance electrons to make an overall reaction. So in that case, we'll have to multiply this by 2. So multiplying this by 2 and then adding, so here we get 2, here we get 2, and here also is 2. So the 2 electron gets cancelled off on both the sides. Now adding these two equations, what we get is an overall equation. So 1 MnO4 2 minus and then 2 MnO4 minus will give us 3 MnO4 2 minus, that is manganate 6 ions, plus we have 4H plus as such unused, so we'll write that also. The electrons are got cancelled off, so the remaining part is now MnO2. So let's write MnO2 plus 2 MnO4 minus, which is here. So 2 MnO4 minus, and then we are again left with 2H2O, that is 2 water molecules, so that also will write. Now just check if we are left with any species which we have forgotten writing. So no, it's all done. We have added also that in a correct ratio, that is 1 MnO2 and 2 MnO4 minus. So yes, this is what we have written. So multiplying and writing the correct value is also important. So this is an overall reaction for our equation shown here. The second part is that suggest and explain how the E cell value of the disproportionation reaction changes with an increase in the pH. Now let's have a look at the equation here, this equation where H plus is used. Now understand, increase in the pH means decrease in the H plus ions, because the acidity decreases with the increase in the pH, right? So that shows that the concentration of H plus ions decreases with the increase in the pH. So if the H plus ion decreases, the equilibrium is going to shift the left side, and if the equilibrium shifts left side, the positive value is going to get the less positive value. If the less positive value is used here, the subtraction of this equation and the other oxidation equation, if we do the subtraction value, that is the answer after subtraction will also decrease because the bigger value has decreased. Right? I hope the point is very clear that with the increase in the pH, the concentration of H plus decreases. As the H plus ions decreases, the equilibrium shifts left side. The equilibrium shifts left side, producing more electrons. The positive value becomes less positive. So if the bigger value decreases, the subtraction value, that is the value after we get the subtraction, also decreases. So how is the E cell value? E cell value going to get affected? The E cell value decreases as with increased pH, the concentration of H plus decreases, equilibrium shifts left side, making E standard value, now E value, making E value less positive. I explained everything, but it carries 1 mark, so even if you write it in short, it's acceptable and you will get the 1 mark. So here ends the question 2, and let's start with question 3 now. Question 3. Question 3a is carbon disulfide CS2 is a flammable and reacts readily with oxygen as shown in the reaction 1, and reaction 1 is given here where carbon disulfide is reacting with oxygen to form carbon dioxide and sulfur dioxide, and the balance reaction is given here, and we are given some content, some data in this table. Let's see what's that the table 3.1 shows the standard enthalpy of formation and the standard entropy for some substances. So these are the reactants and products participating in the reaction here, and the enthalpy of formation and entropy of each of these substances are given here. And the question is, calculate the standard Gibbs free energy change, that is delta G, in kilojoules per mole for reaction 1 at 25 degrees Celsius. Now if we talk about delta G, we have the formula delta G is equal to delta H minus T delta S. Obviously for that we need the enthalpy change of the whole reaction, and the enthalpy of formation is given here. And we need the temperature and delta S, that is entropy change for the reaction. Now if we talk about enthalpy and entropy change, here is the reaction 1 given. So let's start by calculating delta H reaction, that is for this reaction. So that's product minus reactant for the enthalpy of formation. So if we start with the products, carbon dioxide enthalpy is minus 393.5 plus it is 2 SO2, that is twice sulfur dioxide. So we need to multiply the value of sulfur dioxide with 2, that is minus 296.8. Now this is for the product minus reactants. So for reactants we have carbon disulfide, that is 116.7. so that is for reactant. That's all. Oxygen is an element, so enthalpy of formation for oxygen element is 0. Now that is equal to minus 1103.8. Now we know that the enthalpy change is given in kilojoules per mole. So the enthalpy change here is also calculated in kilojoules per mole. Now if we start by calculating the entropy change of this reaction, again it is product minus reactant, and we have to start with the carbon dioxide and sulfur dioxide. So again in the same way we have 213.8 plus again the value of sulfur dioxide has to be multiplied by 2. So 2 into 248.2, that is for products. Now minus the reactant values. So carbon disulfide again is 1. So we have 237.8 plus the oxygen's value. Now that has to be multiplied by 3 because here it's 3O2. So again 3 multiplied by 205.2. So this is how we calculate the entropy change, and that is minus 143.2 joules per Kelvin per mole. So this is how we calculate. Now and understand this is entropy is in joules and our enthalpy is in kilojoules. So we need to convert the joule into kilojoules when we substitute it for the Gibbs free energy, that is delta G. Delta G is delta H minus T delta S. So if we substitute the values, okay, let's substitute the value for delta H reaction and entropy change. So that is minus 1103.8 minus, now temperature is given here 25 degrees Celsius, but if we convert that into Kelvin, we have 298. Again 298 into entropy change, but this time entropy change has to be in kilojoules. So if we convert that, it is 0.1432 entropy because we divided it by 1000 to change it into kilojoules. And the answer is minus 1061.1 kilojoules per mole. So that is how we calculated the Gibbs free energy change. So here I'll write the answer, that is minus 1061.1. so understand this is kilojoules, so we need to convert the entropy change which was in joules to kilojoules by dividing it with 1000. Let's go ahead with the next part B. Carbon disulfide reacts with chlorine to form tetrachloromethane as shown in reaction 2. So here is reaction 2 where carbon disulfide is reacting with chlorine to form tetrachloromethane and the other product which is given here S2Cl2. Calculate the maximum temperature in Kelvin for reaction 2 to be visible. Now if you want to calculate the temperature at which the reaction becomes just visible, right? So in that case, as we can see here, the enthalpy change and entropy change both for the reaction is given. We need to understand that in that case the Gibbs free energy has to be taken 0. Okay, so if we substitute all these values, delta G is equal to delta H minus T delta S. Okay, so here delta G has to be taken 0. Substitute the values here. Enthalpy change is minus 261.6 minus the temperature, and the entropy change is minus 365.5. So now if we rearrange the equation and calculate T, okay, again we made one mistake here, is that the entropy change has to be divided by 1000. So again it is minus 0.3655. So here there is no decimal and the decimal is here. So if we rearrange now, then it's going to be T is equal to 261.6 divided by 0.3655, and the answer is 715.7 Kelvin. So 715.7 Kelvin is the answer. So you can understand that. Remember always, if you want to find out the temperature at which the reaction just becomes visible, in that case delta G, that is Gibbs free energy, has to be taken 0. Rearrange the value to find out the temperature, and in that way you will find out the temperature in Kelvin. So here our question 3 ends, and I hope question 1, 2, 3 all are very clear. In our next video we'll be solving question 4, 5 and 6.